Okay, are we recording? Yes, we are. Okay, so hopefully what I write on the board will show up on the video, but you never know, as we saw last semester. Okay, so quick run through of the syllabus. Now, all of you, hopefully, presumably, have taken some linear algebra course, perhaps when you were an undergrad. And while a lot of important mathematical skills were taught in a class like that, the way it's normally taught gives you a very unrealistic idea of what linear algebra is about, because what are you doing? What you can reasonably do by hand. Solve systems of maybe 3 or 4 equations, or solve other problems involving, at most, maybe a 4x4 matrix. But problems in linear algebra pop up in a great many applications, one of which I'll illustrate for you very soon. And so it's one of the most fundamental areas of applied computational mathematics. But in this class, the idea is we're solving problems for which a computer is doing all the work, and therefore solving a great many equations or working with extremely large matrices. So a lot of the ideas that you'll learn about in a linear algebra course come into play, and some of these things, especially from early on in the class, will be familiar to you. But when you have large-scale problems like that done on a computer, there's new issues that come about. So basically, we're taking what you know of linear algebra from before and making it real. So I'm going to cover, it's kind of a review of methods for solving systems of linear equations, like is taught in a ordinary linear algebra course, except with a computer involved, which, as I said, changes things. That'll be the first part of the course, and then I'll get into solving more troublesome systems of linear equations, which are least squares problems, and then also iterative methods for solving systems of equations, which are not normally covered in a linear algebra course, because these are strictly numerical methods, but they're especially useful for large-scale problems. And then eigenvalue problems, which you may have learned about eigenvalues in the first linear algebra course. So realistic practical methods for solving those problems we'll see. Toward the end of the course, we're going to look at some applications du jour, current mathematical fads. Everybody's talking about neural networks and machine learning, which have some numerical linear algebra ingredients in them. So we'll take some time to introduce you to those. Okay, now, you'll see on the syllabus, there's a course website, and I sent an email to all of you with that. So that's going to be a very important resource for you, because all these times will be posted there, other materials will be posted there. So be sure to bookmark that for the semester. The prerequisites, so officially prerequisite is Math 326, and it says, and knowledge of eigenvalues and eigenvectors. I try to assume as little knowledge as I can. Also, some of these things may have been seen years ago. So I try to take time to review things. Let's see. As far as the textbook is concerned, I talked about textbooks in the email that I sent. So as far as lecture notes, what I tend to do is I write up my lecture notes quite neatly, and then I ahead of time and follow them very closely in class. So on the course website, I do have a set of notes that I've used in this class in the past. So you can certainly, there's going to be, yeah, Hattiesburg campus closed tomorrow.
Ooh.
Okay. Well, that's good to know. Okay. Well, I wasn't really ready to teach my Tuesday class anyway, so. All right.
Praying for frozen roads on Wednesday.
No.
Yeah.
I want class to happen on Wednesday because it takes a lot of time to get the schedule rigged up just right. If we have a day lost, then I have to
You can
redo the whole thing.
video with the cats at home. Just kind of post it that way.
It's not cats
Cat.
anymore.
I'm sorry.
Okay.
I know. As soon as I said the S,
Okay.
I was like,
Okay. So I'll keep that in mind. So you can certainly refer to those notes, but those materials in those notes ended up going into my own textbook that that was published last year. Some of you may, or actually several of you may have that from a previous course, but it's up to you as to which resource you want to use. But certainly the notes that I have on the site, I'm going to be covering that same material, so that would certainly suffice. We also have the official textbook by Demel, Applied Numerical Linear Algebra. I will be using some problems from that book, but I'm going to repost those in handouts. But I also have a bootleg copy of a book as a PDF for those of you who want that. So just let me know. So number, like I said in the email, you don't have to purchase a book for this class. Okay, there are no tests in this class. It's homeworks that will include, but there will be a programming component, so there will be some programming problems. What I've historically done is that the last assignment of the course includes a significant programming project. So something to look forward to. Now, I don't require anyone to use a particular language, but the probably easiest language to use for this course is MATLAB, which many of you have used from a prior course. So my textbook has a MATLAB tutorial in it for those of you who haven't used it before. MATLAB is now also freely available to all USM students because the university now has a site license. Because normally before that the student version was $50, but you don't have to do that anymore. So if you have any difficulties, technical issues getting up and running with that, please let me know. Now, we're not going to jump into homework assignments very quickly in this class, is because the first thing I'm going to be doing during the first, 2 weeks, depending on whether we lose tomorrow due to winter weather, is this chapter of that was also covered in Math 561, which a large majority of you took. So I'm not going to collect problems from that chapter because it's going to be review for some of you or a refresh of linear algebra for the rest of you. I will recommend problems, and certainly if you want to try working them out to test your understanding, then I will be happy to look over them for you. But I'm just not going to require them as part of a grade. Now, I know that leads to a mentality of, oh, well, I'm not going to do them. You are graduate students now. Mm-hmm. Different mentality is called for. So if you're feeling rusty, well, it's really loud. Okay. That keeps happening. I'll be closing their door too. Well, one thing I will do that I've done in past classes on numerical analysis is, in addition to the homework problems that I'll give from various sources, I also have given quizzes on Canvas that test knowledge of certain concepts. So I will be assigning some quizzes on Chapter 3, but not actual exercises from those. So that's one thing you'll need to do to make sure that you're ready to roll when we get to the other chapters. So sometime this week I'll put out the first Canvas quiz. And with the quizzes, that's something where you go ahead and submit it, and I'll grade it, and then you do have a chance to go back and try again if anything you got wrong. So there's no reason that you all shouldn't like end up eventually acing the quizzes. Okay. Any questions about how the course will be run? Historically, we've had like 4 or so assignments. The course is a little different this time, so it may work out a little differently, but that's a general idea. So it works out to roughly 1 per chapter. Okay. Oh, there's the Eagle alerts. Yeah, I'm going to be notified 5 different ways that there's no school tomorrow.
We're going to have a phone call here soon.
Yeah. Yeah, and text messages and the works. Okay. Now, so what I will try to do after class is over, so yeah, during our meeting, is when I'll start uploading the video from each class. So hopefully by that evening, it'll be on YouTube. And what I will do is on the course website, there's a lectures page that holds the whole schedule, and I will post a link to the YouTube video on the lectures page as soon as it's uploaded. Okay, so if you miss class, you'll be able to stay up to date with things, but better not to miss class.
I'm dead.
Well, okay. All right. So since this is a numerical linear algebra class, yep. Well, it's good that they make sure we really, really know that.
Oh yeah.
There's
no class.
Yeah.
Everyone's paying attention to that anyway.
Okay. So since this is numerical linear algebra class, I'm gonna take some time to talk about partial differential equations. I want to emphasize before I go into this is a preview. So really this is just to give an idea of how problems from numerical linear algebra arise. So I'll explain everything as I go, but I'm going to be using, the other point I'm going to be making is that this subject is not an island. So numerical linear algebra relates very closely to other areas of mathematics, and it relates to other branches of numerical analysis also, which you see in other courses offered in this program. So this will give you an idea of how all of that ties together. So what I'm going to do is I'm going to start with a problem that seems at first glance to be very far away from numerical linear algebra, but then I'll show you how numerical linear algebra can be used to solve it. Whoops, totally got my words mixed up. Initial boundary, this is not going to go well. But that's what I get for having class at 4:45 in the afternoon. Okay. So this may relate to things you're seeing in other classes. So I have a PDE, partial differential equation. I feel like writing it out. In this case, the heat equation, which is du dt, is equal to some coefficient, I'll call it alpha squared, uxx, so second derivative of u with respect to x. And I'll just pick an interval to define the problem on, say 0, 1. And positive t, so this is how a problem like this is normally described. And then that's only one ingredient of my IBVP. Then I have initial condition. Don't ask me why I wrote my I's in 2 different ways. So IC, initial condition. So at time 0, t equals 0, we have some given function f of x that solution is equal to on the interval 0, 1. And then we have boundary conditions, BCs. Now, there are different boundary conditions I could choose. I'm just going to that the solution at the boundary point, so x equals 0 and x equals 1, that the solution is 0 at both endpoints. Now, U, for a heat equation, U refers to temperature. So if we're simulating the diffusion of heat within a one-dimensional object, like a rod, then I'm specifying what the temperature is throughout the rod at the initial time. And I'm specifying that the temperature must be 0 at both ends of a rod for all time. So with those conditions, how does the temperature change over time? Now, physically, you would think that over time, with no external heat sources or anything, the temperature will eventually cool down to 0. And in fact, that is what will happen. And the thing is, a problem like this, something you learn in a course such as Math 517 or Math 606, you can write down a formula for a solution, but I'm going to use this to illustrate how you use numerical methods in a role that numerical linear algebra plays that would also apply if you have a PDE that's more complicated than this, that could not be solved analytically using techniques from those other classes. So, how am I going to go about, what I want to do is try to obtain a system of linear equations that would help me solve this problem. And it will be a system of linear equations because this is a linear PDE. So if it was a nonlinear PDE, I'd have a nonlinear system to solve. Okay, so how am I going to go about this to get from PDE land to numerical linear algebra land? That's going to be really distracting. Only slightly less distracting. Okay. There's a process that occurs very frequently in numerical analysis, so something that you should be aware of, called spatial discretization. So what that means is I'm going to, instead of my solution u being a continuous function of x and t, I'm going to describe it on a discrete domain instead of a continuum, because in the original problem, I have a problem defined on a continuum. All x between 0 and 1. All t greater than 0. So now I'm going to make a discrete domain in space only for now. So I'm going to actually, before I do that, I'm going to work with the interval 0 to 1, my spatial domain. I'm going to select equally spaced grid points. So I'm going to call my this point x equals 0, that's x naught. This is x1, x2, x3, and so on. There will be uniform spacing between points, delta x. And I'll have x1, x2, up to x capital N. And then my other boundary point will be x n plus 1. So that means that my spacing is the width of this entire interval, which is 1, over the total number of subintervals, which is n plus 1. Okay. So then I can describe these grid points, xj, as j delta x. for all j starting from 0 up to n plus 1. Now, I already know what the solution is at these endpoints. It's 0 because of my boundary conditions. I need to solve for it at these other points and for all time. So what I'm really going to solve for is u sub j of t. So this is a function of only t now. And that is an approximation of my exact solution at some fixed point xj. And this is also for all the interior points. So instead of describing a function of two variables, x and t, I now have n functions, each one of one variable, only t. So this is how I've discretized only in space, not in time, not yet. So now I'm going to solve for these, because what I'm going to do is, instead of having one PDE, partial differential equation, I'm going to derive from that a system of ODEs, ordinary differential equations. So how would I do that? Use a finite difference formula to approximate this second derivative of u with respect to x. And I'll just give you what the formula is. So this is something that comes up in classes such as Math 560 or possibly 772. So uxx at a certain point xj and whatever t I have is equal to, so a finite difference formula, I could use many different ones, but I'll use, this one is most convenient. It's called a center difference. All over delta x squared. Now, so my uxx is equal to this. This is the center difference plus some error, and I write big O of delta x squared. What I mean by that is the error in this finite difference formula is proportional to the grid spacing squared. So as delta x goes to 0, I use more and more grid points. The error goes to 0 quite fast because delta x is being squared. So in other words, if I use 10 times as many points, so delta x shrinks by a factor of 10, the error will shrink by a factor of 100. Okay. So now I can take the uxx part of my PDE and I'm just going to replace it with this. Now, keeping in mind though, let's suppose that j is equal to 1. Well, here I have u0, which I haven't defined here, because I have this defined only for j equal 1 to n. But that's where I use the boundary conditions. So u0 of t, 0, un plus 1 of t is also 0 because of the boundary conditions. So that way, this is defined, well defined, for all indices j from 1 to n. So we're going to first see the first whiff of linear algebra when I take this expression by approximation of uxx and substitute it into this PDE. Of course, whoever's watching this at home didn't really see me just do that. but you're all here, so it's okay. But I'll show you how that's done and what we get out of it. So now I have, since I have a derivative with respect to time, I need a time derivative of all of these. So that's so I'll write again the PDE that I just erased. So for the left side, I have a time derivative, so I have a time derivative of all my functions that represent my solution that I'm looking for. Okay. Then, on the right side of each equation, I'll have my alpha squared. And then I'll have my approximation, my finite difference, for replacing uxx. So I'm going to have u0, which is 0, minus 2u1 plus u2 all over delta x squared. So this is the approximation of uxx at x1. And then I go to the next line, do the same thing for plus x2. So I have u1 minus 2u2 plus u3 over delta x squared. And I keep going, all the way down to the second to last equation. So u(n minus 2 minus 2u(n minus 1 plus u(n). And then for the last equation, just like the first, I have to take the boundary conditions into account. T minus 2un plus 0, because of a boundary condition on the right boundary. So now for my PDE, I have a system of ODEs to solve. Now, when you're solving an ODE, what other information is required? Who remembers? Because an ODE by itself does not have a unique solution. What has to be included with it? Initial condition. In this case, all these would have initial conditions. So u1 of 0 would be f of x1. And the same for these others. So the initial condition from my original problem at u of x0 equals f of x. So I'll just fill that in. For all of these. So now what I have here is a system of ordinary differential equations. So all this is an IVP. It's an initial value problem. The boundary part has been taken care of already because I accounted for that in my approximations of uxx. So that's out of a picture now. So my PDE is now a system of ODEs. But what I'd like to do now is describe this in a more concise form than this. And this is where linear algebra helps. Notice that all of these systems, all the ODEs in the system are coupled together. Here I have u1 prime, but the equation involves u2. My equation for u2 prime involves u1, u2, u3. All the unknowns are coupled. You cannot solve these equations independently of one another. However, the dependence is a relatively simple one in that each of these unknowns depends linearly on the others. So u2 prime is a constant times u1 plus another constant times u2, another constant times u3. And the same applies for all the other equations. So what that means is I can describe this system of ODEs in matrix vector form. I just need to introduce the right notation for that. Okay. So I can find a vector quantity, u of t, to consist of u1, u2, etc., all in order down to un. And similarly, the vector f consists of values of f at my interior points, x1, x2, xn. Then I can describe my system of ODEs this way. U prime of t is equal to a matrix A times u of t, and the initial condition, u of 0, equals f. And the reason I can do this is what I mentioned earlier, that each of these unknowns in this side depends linearly on the unknowns u1 to un, as we can see from the equations written over there. You take what the coefficients that are multiplying u1, u2, etc., and recognize it as a matrix vector product. And the matrix, in this case, is we have alpha squared, because that's, as you see, that's multiplying everything. We also have delta x squared in the denominator. You see that's in every equation, again, multiplying everything. And then the matrix looks like this. We have minus 2's all the way down the main diagonal. And then we have 1's above, 1's down below. All other entries are 0. I'll fill in a few more here. Okay. Now, how you can see this, a good example is what I have written over there, u2 prime. So I have alpha squared over delta x squared as a common factor. And I have, because if I just write this vector u over here, how do you do matrix vector multiplication from your linear algebra course? You go across each row, down the column. I'm multiplying this by this, because I have a times u. So I'm multiplying this times this times this. I keep going across this row, down this column, and adding them all up. That's this matrix multiplication. So if I look at the second row, for u2 prime of t, what do I have over there? I have alpha squared over delta x squared, u1 minus 2u2 plus u3, and then there's no dependence on any other u, and that's why the rest of the row is 0. So we see at most 3 non-zero entries per row, because those are the only unknowns that are dependent on. So, so anytime you have that kind of relationship where you have linear combinations of variables, that you can think of it as a matrix vector product. The coefficients from a linear combination are the matrix entries. Any questions about how this matrix fell out of this? So it's important, the helpful skill to be able to recognize, oh, I have a matrix vector product here. Anytime you have a kind of linear relationship, you can think of it that way. So now a little bit of linear algebra has appeared. We have this matrix here, but now I still need to solve this system of ODEs. And how am I going to do that? Well, I've only discretized so far in space. Now I'm also going to discretize in time. So I need to approximate this time derivative here, just as I approximated uxx earlier. And that will get me to the kind of problem we're going to spend a lot of time talking about in this class. Okay. So what I will do is I'm going to solve a system of ODEs using very many time-stepping methods I could choose. One that would be quite relevant to this class would be called backward Euler, which is u at tn plus 1 minus u of tn over delta t. So this is my approximation of u prime at time tn plus 1. This is called a backward difference because we're figuring out the derivative at time tn plus 1 by using information further back in time, as opposed to forward in time, which would be a forward difference. Okay, that is approximately equal to the matrix A times U plus, at Tn plus 1. So what I did was I evaluated the system of ODEs at time Tn plus 1. Now, Tn is equal to n times delta t. So delta t is some chosen time step. So we pick that. And we're going to solve for u of t at certain uniformly spaced times, t1, t2, t3, etc. And keep in mind that u of t naught, that's u of 0, is already given. That's f for my initial condition. So I can rearrange this u of tn plus 1, and then I'll move this over to the left side. So minus a tn plus 1. And then I'll take this and move it over to the right, multiply by delta t. Oh, whoops. This should be multiplied by delta t. It's equal to, oh, actually, this is not multiplied by delta t, u of tn. So u of tn is known. U of tn plus 1 is our unknown. So now you're going to factor it out. Now, with linear algebra, you got to be matrix multiplication. You got to be careful. Order matters. I can only factor out un plus 1 to the right. So I can write it this way: identity matrix minus delta t a times u of tn plus 1 is equal to u tn. So now I have a numerical linear algebra problem, a system of linear equations to solve, often described using generic notation ax equals b, where this is the matrix of the system, identity minus delta t a. This is my right-hand side, often referred to as a vector b. This is my solution, often referred to generically as x. So that's my ax equals b problem. So what I can do now is, if I start with my initial data over here, then I solve the system of equations and I get u of t1. Then I substitute that over here, the right side, solve for u of t2, and I keep going. So now I'm solving a system of equations repeatedly to solve my initial boundary value problem at these selected uniformly spaced grid points x, at these selected uniformly spaced times in Tn. So if a number of grid points, n, capital N, is very large, this becomes a difficult system to solve because you got to do it on a computer. It's not practical to do it by hand. And each arithmetic operation on the computer has some error to it. So the problem becomes more and more sensitive to round-off error, which is something you'll see why when I get to that topic. It'll be next week sometime. And there's various methods that could be learned in a linear algebra course, Gaussian elimination. But there are also iterative methods that we'll learn about that may be a better choice, because Gaussian elimination presents a whole host of problems. In fact, back in the 60s or so, when it was first being studied, and electronic computers were first out, and not very well, and properties of arithmetic, computer arithmetic, not very well understood. People seriously thought that Gaussian elimination was, which had by then had already been used for ages for solving problems by hand. People really thought it was unstable, numerically unstable, could not be used by computers until leading figure in numerical linear algebra by the name of Jim Wilkinson took the time to actually prove that it was stable. And that's why it's still used today. Otherwise, he would have junked it. That would have been very bad. So, all right. But and the thing is, something like system linear equations, you learn about how to solve it in a sophomore level course. You think, oh, okay, move on to harder problems. But it actually is a really hard problem when you are looking at a realistic setting, when you have a great many equations and a computer has to get the job done because of all the different errors that can creep in and how you prevent them from getting out of control. So that's one of the major themes of this course, is how do we rein in that error that computer arithmetic causes when you have to perform a zillion operations. All right, so another thing is, if you're solving a problem like this, well, you're actually solving the system of equations, the same matrix, but a different right-hand side as you keep time stepping. So is there a way to save information from when you solve the system the first time so that you can solve it more efficiently the next time? You should not see each problem as in a vacuum. You want to be able to engage in the kind of reuse whenever you can. And that's something that will come up very soon, too. So I just wanted to give you an idea of kind of problems from other areas of mathematics where numerical linear algebra plays a central role. So it's this problem right here that will be devoted to chapters 3 and 5, and then other fundamental problems from numerical linear algebra, like least squares problems, eigenvalue problems, chapters 4 and 6. Now those chapter numbers for chapters from my book, which is what I put in the reading schedule. But those of you who want to use the notes, the older notes that are posted on the site, I'll indicate what chapters those refer to instead. I just haven't gotten around to doing that yet. Okay. How much time? Okay. 48 minutes. Okay. Dang.
You're the boss,
though. Yeah. Okay. All right. Well, I just want to take a really short, like 5-minute break, and then because this is a good break point. Because then I'll start covering like material about system linear equations during the rest of today. So, okay. Keep in mind, I'm still recording because I don't want to stop it. Pain to splice multiple video files together.
Yeah, he has to. Carly's pen.
Oh.
I'm just looking for my materials. Oh, I really like Grace's pen better.
Oh.
We're gonna lose another one. I don't
That's what I was thinking too.
Is that my?
Yeah.
Teresa.
Yeah, show them my
That's what I was thinking too.
Is it in here?
No, not in her bag. I'm saying it could feel under the.
Under the
Yeah.
leg?
Yeah.
I come from my leg.
Yeah, look, try looking in mine. We'll see that. We're finding on the last day. We'll find your last. Yeah, I think you were just trying to get my pen. I mean, she does make really good pens. I do. I keep the best. I really like this pen, so everything happens for a reason. Yeah, you can have that pen. I've got like 15 others.
So now it's going to be more or less on YouTube, but looking for your pen.
I mean, I don't have another on me. I've got like 7 in my purse. Wait, what?
Did you want me to call it?
No.
Yes, I told you. To give you my nice expensive one. That's what it was. This is crazy. Yeah. I mean, it's very Carly thing. Yes, that's what y'all take my eyes of our pen. Put my pen down. I'm gonna really take this for
Okay.
What's my pencil?
Must be a YouTube, like a writing utensil.
So you said ED Rome?
What?
ED Rome?
Right. Oh. Another option, USM Public would work.
I clicked on that one also.
Oh.
This is my school computer, and then I have a firewall on it.
Oh.
I'll text my tech guy and ask him.
Figures.
Yeah.
So people having trouble with that concept?
They're already sending
No,
questions.
as soon as that email came out, the students asked me, "Is the math not going to be open tomorrow?"
I just wouldn't respond.
Not.
Just wouldn't reply.
Okay. Well, now it's 6 minutes have passed. Okay. So, we're going to do a review of Gaussian elimination, which you would have seen in another course, but unless it was a numerical analysis course, it'll look kind of different. And maybe use some different terminology. So, I'm going to focus on a so this is, so if you're referring to my textbook, is section 3.1, and if instead you're looking at the notes that I posted on my 610 site, I'm just going to look it up in a table of contents real quick. Oh, that's also section 3.1, so that worked out beautifully. Okay, so we're looking at a generic system of linear equations, AX equals B. Now, as a reminder to those who people people tend to get too caught up in notation in terms of what letter is used for what. And a reminder to not do that. A friend of mine was a faculty member at Stanford, where I got my PhD. Okay, most of you know that, but still. She was teaching a numerical linear algebra course, and she had some students come up to her after the midterm exam, outraged because they complained that she had put a problem on the midterm for solving CX equals D, and you only told us how to solve AX equals B. So,
Yeah, I would have been like, you deserve that one.
yeah, so don't do that. Those were Stanford students. Like, what's wrong with them? What's wrong with admissions over there? So most people refer to it as AX equals B. So just for completeness of the notation, now the matrix A, assume is real, n by n matrix. So I am assuming that A is a square matrix. It will not always be the case through this course. There will be times we deal with rectangular matrices, but not now. X and B are vectors of length n. Now, I want to emphasize, in the linear algebra world, or sort of the numerical linear algebra world, by default, we think of vectors as column vectors. So X and B, you can think of them as vectors of length n, but also you can think of them as matrices that have n rows and one column, and that's how I'll write them. So first A has these entries, and this would be my common notation convention, where I use first index refers to a row, second index is a column, and I'll use uppercase letters to refer to matrices, and then the corresponding entry of a matrix I use the same lowercase letter. So it's very common convention. Although mathematicians never agree on these things. And to give you an idea of how bad that is, you probably all know of, as it comes up in trig, quadrants. You divide the xy plane into, you all know what that is. First, second, third, fourth quadrant, right? Okay. Well, now think of 3 space. You have x, y, z axes. Divide 3-dimensional space into 8 octants. Now, everyone is agreeing on what the first octant is. That's where x, y, and z are all positive. We do not refer to octants 2 through 8 because no one can agree on what they should be. So we just don't bother. All right, so this is how I refer to the entries of A, and then X is column vector of x1, x2 up to xn. I use lowercase letters to refer to vectors. So then Ax equals B, the matrix vector product and the definition of a matrix vector product. So matrix A times the vector X is a vector. So if I want to refer to a single element of this vector, this is a formula that defines matrix vector multiplication. So notice in this summation, we're summing over j, all j from 1 to n. And notice that the column index is j, and the same as the entry of x that we're referring to. So if I'm multiplying a by x, I'm going across the row down this one column. So notice the second index, 1, 2, 3 up to n, 1, 2, 3 up to n, are being multiplied together and all added up. So one of our fundamental operations. I should mention that in both the notes in the book, there's a appendix. It's a review of linear algebra. Or actually, in the notes, it's up front. It's like the first chapter. So if your linear algebra is a little rusty, by all means, take some time to look through that, and it goes over all of these essentials. Now, if I were to write out the system of equations in a laborious entry by entry form, so there's a first equation from a system Ax equals b, and then second equation, all the way to the last equation. Now, the idea is we want to be able to have a nice, efficient, systematic way of solving any system of equations of this form, assuming it has a solution. So, in other words, the matrix A, we're going to assume is invertible. And if it is not, then the algorithm we finally developed for this, which you'll see on Wednesday if we're here, will naturally break down. Okay, I have 28 minutes. That'll work. So, considering that the unknowns, x1, x2, xn, these equations couple these unknowns together. So, so I can't solve these equations independently of one another. It'd be great if I could, but can't do it yet. So, when you're first learning about systems of equations, like many years ago when you maybe had just two equations to solve, you carried out this process of elimination and substitution. For example, I could take this equation, rearrange it, and solve for x1. And then I could substitute that expression for x1 into the other equations, and therefore eliminate x1. And you keep doing that until you get down to one variable, solve for that easily, and then substitute and get all the unknowns. So that's the general idea here. And that is the kind of process that I will describe. But again, it's got to be something that is systematic enough that you could tell a computer how to do it. Like writing a MATLAB program for it, or whatever language you want. But I also want to present this problem of solving system linear equations in another way that will serve you well when trying to attack problems like this in general. And there's a couple key questions that are worth asking to come up with such a systematic method. So some of the most important questions you can ask in general for algorithm development. So this should just become a natural way of thinking for you to get into this line of work that I've enjoyed doing for 30 years. First, if you're trying to solve a problem such as Ax equals b, a good question to ask yourself is, for which kind of problems within this class? So if you're examining all square linear systems, which systems within that class are easily solved? What are your simple cases? And so then you can narrow down your space a little bit, like just to figure out that simpler problem. Or sometimes mathematicians take this idea a little too far. That leads to the math joke about consulting all these different kinds of scientists to figure out how to get cows to produce more milk. And after it doesn't work with the biologists and the chemists and so forth, he turns to a mathematician. He says, "I'll show you how to increase milk production by 300%. Step one, assume a spherical cow." And that's why we need the second question. Well, in that position, stop at the first. So once you solve the easy types of problems, how can general case be transformed, or maybe a more informative word to use, be reduced to one of these easy cases? So in other words, if you solved a problem for a spherical cow, can you make all cows spherical? And if so, then great. So we want to identify certain types of matrices A for which we can easily get the solution to AX equals B. And then once that's established, how do we reduce, in the case of a general matrix A, at least one that's invertible, to those easy cases? So here are some easy cases. Now, one common thread between them is that at least one equation is made independent of the others. So that way, you can just solve that one equation immediately. So a few types. A is upper triangular. Now, the term upper triangular is going to be very important to us in this class, and I hate writing it out all the time. So I will use this symbol, that, to refer to upper triangular. That's enough right to write out as this. And we also have lower triangular. Which I also have a symbol for. Now, I should give formal definitions of these. Upper triangular means Aij equals 0 if I is strictly greater than j. So the row index is greater than the column index. So all those entries below the main diagonal are 0. Lower triangular is the opposite. Aij is 0 if I is strictly less than j. And then if you put the two together, there's a message from my wife at preparation for a storm. The lines at Winn-Dixie in our places are really long. So if you're trying to get some supplies after class, then good luck. Okay, and then if you put the two together, you have a diagonal matrix, so something like this. So Aij equals 0 if I is not equal to j. So for an upper triangular system, so I'll give a upper triangular system, something like this. X1 minus 2x2 plus 3x3 is equal to 4. 5x2 minus 6x3. Yes, I'm being very lazy making up these numbers. Is equal to 7. And then 8x3 is equal to 9. So in this case, the third equation can be solved independently of the others. You just get x3 is equal to 9/8. So if you take a value of x3 and you substitute it up here, now you can easily solve for x2. So in other words, you've made a second equation independent also. And then you solve for x2, and then both values, x2 and x3, get substituted into the first equation, and I can solve for x1. Lower triangular is just the opposite order. The first equation is independent, and you just do a simple division, and then you substitute down from there. So the process I've just described is called back substitution. Whereas for a lower triangular system, you could use forward substitution. It works the same way. Diagonal system, is completely trivial because all the equations are dependent. You just do n divisions, and bam, you have your solution. Okay, so but we don't need to go that far to diagonal. I mean, reducing a general matrix to diagonal, which is what he did in a first linear algebra course, like reduced row echelon form. Yeah, this is row echelon form right here, and that's enough. As long as you make one equation independent, and then the next equation dependent on only two variables and three and so forth, that's enough that we know what to do at that point. So we just have to figure out how to reduce any matrix A to this point. So now that we settled the first question, what is an easy case to work with? Let's just stick with upper triangular. How to reduce a general matrix to upper triangular form. So, and that's where Gaussian elimination comes in. Now, Gauss, arguably, well, it would be quite an argument, but arguably the greatest mathematician of all time. He's certainly way up there. Maybe look at the top three, maybe. Had a lot of things named after him. But this one, he did not have anything to do with. He played no part in inventing Gaussian elimination. So someone got really gypped there. I believe that there are records of it being used in China like thousands of years ago. Gauss was around a little bit after that. So I remember seeing a presentation in which I could remember like how his name got attached to it. And he's probably like, all right. By contrast, my advisor, Gene Golub, refused to have an algorithm of his own making named after him. So about a month after he passed away, it was done. So,
He rolled over in his grave.
yeah. Oh well.
Should have put it in his will.
Yeah. That'll teach him. All right. So, well, actually, he didn't do it himself. His collaborator, who was still alive, has his name included too. And I guess he's like, okay, fine. Yeah. So I'm not bothering to name my method after myself. But I guess if one of my students wants to after I'm gone, then I can't stop
You
him.
can't stop it.
Yeah. Okay. So the idea is use a general invertible n by n matrix. So of course, to be invertible, it has to be square. To upper triangular form. Okay. Now, the goal here, and I hope I can accomplish before class is over, maybe, is not just to describe a process, which you would have seen before, but also like describe an algorithm. So I'm going to do this in more code-like terms. So if I have my matrix, and I often use generic notation to indicate any kind of matrix using x's to refer to non-zero entries. So I don't feel like making up numbers. And the idea is I want to zero, like in this first column, I want to zero out all entries below the main diagonal. Then I want to move to the second column, zero these out, and zero these out. And I have to do this in such a way that the solution, because I can't just put zeros in there. I'd love to, but, and actually a student in my class on this material back at Stanford advocated doing that. Okay, he was joking, but still. In such a way that the solution of the system of equations is not changed, because we're trying to transform the original problem, ax equals b, into an equivalent system that's upper triangular. So what we use are row operations. Because what you can do is, if I do row I is equal to itself minus some number m times row j. So if you add a multiple of one row to another row, add, subtract, doesn't matter. And this is on both sides of the system of equations. Because you're performing algebraic manipulations on both sides. So of course it's going to keep the solution the same. So this is one operation that we can do. Other operations would be interchanging rows, which I'll talk about Wednesday, or scaling a row. But this is the operation that's by far the most useful to us, because you want to figure out what is the right m to use. So that entries are zeroed in A. And not just any entries, subdiagonal entries. So what I'll do is I'll zero all entries in the first column, second column, third column. So since I've decided on an order of events, I'm going to go from left to right, first column to last, and then within each column, go from top to bottom. That gives me a framework for describing this process that translates easily into code. In fact, I can literally write it as code. I'm not going to use any specific language here. So it'll be pseudocode that can be translated into various languages like MATLAB or Java or C or Python. So that'll be my starting point, is the order in which I'll proceed. So here's my algorithm for Gaussian elimination. And we'll see many algorithms throughout the semester, but this is your first one. So I'm going to have a loop that goes from column 1 to n minus 1. So j is going to refer to a column. And the idea is, inside this loop, I'm going to do all my work in column j, and then I'll just move to the next column. I only need to go to n minus 1 because I don't need to eliminate anything in column n. Nothing happens there. And I'll put an n statement down here. Okay. Now, within that column, I'm going to start from the entry immediately below the diagonal and go down all the way to the bottom. So I refers to a row. So the idea is here, the idea is to work on column J. Now, inside the second loop, I'm going to eliminate Aij. So now I is set up to start from j plus 1 to n. I is strictly greater than j at all times, which is what I want, because I want to eliminate all entries below the main diagonal. So how do I carry out this elimination? Using the row operation I described. Now, if I'm performing a row operation, I have to work on each entry within that row. Multiple entries, up to n of them. So I need another loop for that. So I can deliberately leave a little space here. Now, if we take a look at what I did earlier, suppose I'm in this column right here, j equals 2, and then I equals 3. I need to eliminate that, and therefore, because I'm doing a row operation, everything in this row is going to change. So I need to affect these entries. This entry is already 0. If I take a multiple of row 2 and then subtract it from this row, or this row, like for I equals 3, I equals 4, we're only combining 0 entries over here. This will stay 0. I don't need to think about this. So I'm going to work with row 2 in column 2 and subtract multiples of it from this row and then this row for I equals 3 and I equals 4 to eliminate these entries. Now, and these entries will be affected by that row change. So, which columns do I need to touch? K equals J, J plus 1, up to N. Although, in row I, column J, we know what's going to happen to that entry. It's going to be 0. So why actually perform the operation? So I'm not going to do it. It's a waste of arithmetic. And yes, every operation counts. You may have a computer that can perform a zillion operations a second, but you're also having to perform many zillions of operations. So efficiency still matters. In fact, it really matters more than ever. So how I will do this, I want what I have over there. Row I equals itself. So A I K is equal to itself minus a multiplier, which I have yet to figure out, times A J K. So this is row I equals itself minus a M, multiplier M, times row J. And this carries out that operation for each one element at a time. And I had to do this to both sides. So the right-hand side, B. BI is equal to itself minus the same multiplier times BJ. Now, in linear algebra class, it's referred to as an augmented matrix. You have a matrix and you slap B on the right side. That's like an extra column. And you do, so that way you do the same thing to both A and B. So that accomplishes that. Now, the only thing missing is, what's M? What's the multiplier that we use? So I need to fill that in here. Well, I'll show you how we get it. Well, if you look at this row operation, but look at column J, where we actually want to eliminate something. Aij is equal to itself minus Majj. And we want the result of this to be 0. Now, we solve that for M. M is equal to Aij, the entry we want to eliminate, over Ajj. So I'll fill that in here. And in this algorithm, M is referred to as the multiplier. So I'll be referring to that often in the future. Okay. And so recording. Well, it's going to be a huge file. Okay. Let's like up to 6 gigs. I don't have much disk space left, so that could be a problem. So that's it. That's the whole algorithm. That's Gaussian elimination. So you apply this to whatever square invertible matrix A, and this will reduce it to upper triangular form, so that then you can focus on a triangular system that consists of your updated A and your updated B. Because what I've done is I've performed the same operation on both sides, adding multiples of one equation to another that keeps the solution the same. So this is something that you could implement. Now, what if Ajj equals 0? That could be a problem. I'll discuss that next time. That's where we get to pivoting, where you occasionally interchange rows. But what we'll find is that when it's computer arithmetic, there are other reasons besides that being 0 to interchange rows because of computer arithmetic error. Okay, so so the thing is, if this kind of operation, row operation, you carry it out by hand in a linear algebra class. But now you're thinking in terms of code, and you're thinking things one entry at a time. And, excuse me, and remember, computers do exactly what you tell them to. So you have to figure out how processes that you carried out by hand intuitively before, you watch what your instructor did and then just carried out those same steps. But you have to describe things in terms of row and column indices and so forth, and a sequence of steps over what range of indices that describe that it tells you what the indices of your loop should be and so forth. You have to think about all those things. So you have to think like a computer in a way, which is very different from how a mathematician normally thinks. And you break it down into the simplest terms. And the funny thing is, okay, some friends I was visiting when I was traveling during break told me about, because they're in computer science, told me about how one of their programming teachers did a little experiment in class. I think it'd be fun to do, if messy. She brought in all the things you need to make a peanut butter jelly sandwich. And she had the class tell her, tell me how to make a peanut butter jelly sandwich. And it would tell like it'd tell anybody, using very generic terms. But she would take everything he said literally. Like, for instance, open the bread. So you just rip open the bag, and bread goes everywhere. Put the peanut butter on the bread. Well, she takes a jar of peanut butter, puts it on the loaf of bread. The point is you have to be extremely specific and sequential. And I think mathematicians are particularly well equipped to be able to think that way, but they don't think that way automatically. Their math classes don't really train them to do that, even though they should. But I had to think in order to build algorithms. When I examine in classes like this, or 460 and 461, people's code, when they're getting things wrong, it's often because things are being done in the wrong order. But if you can break a task down like I did here, we're focusing on, in this outer loop, we're focusing on one column at a time. Within that column, we're focusing on eliminating one entry at a time. Break down that task into smaller pieces until those pieces are so small that it finally becomes straightforward to write the code for that piece. And you do it to start at a high level. I think, okay, what is it you're really trying to do? Can you break that down into subtasks and then work on each of those? And I found that serves me very well when I'm writing code myself. Those of you who are doing research, or will be, it's a good thing to keep in mind. All right, so the last thing I want to mention is the complexity of this algorithm. Because notice we have 3 loops nested with one another, and each one of those loops can do up to nearly n iterations. So this algorithm requires approximately 2/3 n cubed flops. Flops is short for floating point operations. We were performing floating point arithmetic. So this isn't really that good, because as n gets large, and in places where numerical algebra is used, it does get large, that's very expensive. So we want to look for ways to cut that down, and in certain cases we can. Now, I don't expect you to understand where the 2/3 came from. That takes a lot of work. You have to use like summation formulas and so forth to see why it really is 2/3. So I'm just putting it out there for your information. Because sometimes a constant does matter. Like for some matrices, we can cut it down to 1/3 n cubed. So if you can save half the time, that's good. So that complexity, the runtime complexity, is something that will be very important to us, because sometimes we can, if we can reduce the work by an order of magnitude, then of course we need to do that. Because also one problem that you would have solved in the first linear algebra course is, given a matrix, compute matrix A, compute A inverse. And it's kind of a rule, like a commandment of numerical linear algebra, that you don't compute the inverse explicitly. Because if I'm solving AX equals B, well, X is A inverse times B. If I go ahead and compute A inverse, I can just multiply it by B and I'm done. But that is much more expensive than this, like 4 times as much. And you introduce a whole lot of more floating point arithmetic error in the process. So people just don't do it. So you may have formulas written that way, But when you actually implement them, you're still solving a system of linear equations using a process such as Gaussian elimination. Now, what I will do on Wednesday, and I'm pretty sure we'll be here because I don't think Weber's going to be bad for that long. We're going to take a very different view that would not come up in an ordinary linear algebra class, describing Gaussian elimination in terms of a very important concept of matrix factorization. Because a lot of more advanced algorithm development goes about much more easily when expressed in terms of matrix factorization, specifically the LU decomposition. So that's what we'll get into on Wednesday. All right. I'm sure we're all exhausted. So.